Welcome back to Fat Mama Physics. This is the second part of your vector addition video in which I'm going to be focusing on just problem B in our example. It's a little bit lengthy, heads up for that. And also I will give you one example to try yourself, which is also a continuation of the poor Luke swimming across the river problem. So let's start off with B. Now, before I delve into this problem, first things first, I need to make a few changes to this problem. I'm going to change this problem to, yes, blah blah blah, Seattle is going to be south from directly where the plane was in A, but instead of asking how far east the plane will be, I'm just going to ask you for how long it will take. How long it will take the plane to reach the same latitude that Seattle is on. Now, if that's not clear to you what that means, let me just draw a diagram. Don't worry, I know I just changed it on the fly, the wording's not perfect, but what I'm trying to say is you have a plane and imagine it's flying in that general direction going south, but yes, of course, being affected by the wind and everything. How long will it, and we know that the plane, let's say Seattle is directly south. This is Seattle, and that's separated by 1,450 kilometers. Now, if the plane just flew south, of course it will land in Seattle, no problem. But because of the wind, this plane is going to fly off and it would fly and not be exactly where Seattle is. It's going to be a little bit east of where Seattle is, but imagine if the plane did just continue to fly in that direction, and once it reaches that same horizontal line Seattle is on, or the same latitude, or however you want to interpret it, how long would that actually take this plane to be along the same horizontal line Seattle is? So that's what the question is trying to ask for. There is two ways to solve this, and I will talk about both, but I will talk about some pitfalls that some students will experience along the way. And since this is part B, I'm going to label a few things for us that we already know. We know this angle here is 7.352 . Now, when you're dealing with these numbers, make sure you always use the non-rounded values so you get precise answers. You always round to the last step, okay? So we know this angle, we know how far that is. We know also that this is a right triangle here, and this plane is flying off in this particular direction, off to the side. Okay, now a common mistake a student will make is the student will think, oh, hey, I know my plane is flying at 940, well actually it's more like 937 kilometers an hour in this particular direction. So that means I just have to take 1,450 kilometers and take that and divide it by this velocity here to get my time, and they think they got it. But here's the problem. The problem is you have this 1,450, this is flying directly south. Now the plane isn't flying directly south. It's actually going to fly a longer distance than 1,450 kilometers if it were going at this speed. So we got to be very careful here. Now you could say, oh hey, but I can find this distance, the distance that the plane would have traveled, and use that with our modified speed after the wind to find the time. You could do that, but you cannot use this original distance here. That is assuming your plane is moving south and going as fast as 937.7 kilometers per hour, which is not. Okay, so be very careful of that pitfall. So the first method I'm going to show you is, imagine you know this distance, and I'm going to label distance S because that's in your IB data booklet. It's unfortunately not. A lot of other sources might use D, but I'm going to use S for our purposes. The S as our displacement with a vector there, we need to find that displacement before we can apply the 937. So we do have the angle, luckily. We do have one side of a right triangle. So why don't we go ahead and try to figure that one out. I'm going to use green. Okay. So got a right triangle. Okay. We now, and this S here, we know that's our hypotenuse. We have this angle, and we have, relative to our angle, our adjacent side. So if you have adjacent and we have hypotenuse, the angle, this function we're going to use is cosine. So cosine of our angle, which I'm going to use the original 7.352, this is equal to our adjacent side, 1,450 kilometers, and over our unknown here, which is our total displacement. And we need to solve for this displacement up here by isolating it and getting it to the top, dividing cosine on both sides to isolate it, and we are left with the displacement 1450 kilometers over cosine 7.35 and degrees. Okay, so we can punch that into our calculator. Now here's a function that I think you can check my other video that that shows you how to save answers on your calculator, and that way you don't have to always type it in and oftentimes mistyping or missing things. Okay, so I'm going to recalculate the 7.4 east, and that way I'm gonna save it in that fashion. I'm just going to quickly do it, and I did it by taking the in the other video I took it by calculating it from the inverse tan, and I'm going to store this angle as angle alpha theta. Okay, I'm going to store it as this one. Now I have it saved, so then I'm just going to, I don't have to type everything all over again. So I have 1,150 divided by cosine alpha theta, which I saved that number. So I get the displacement of 1462, and that's probably good enough. 1462 kilometers. And notice it's a little bit further than the 1450, so we do need to use this particular displacement for the new resultant velocity. Okay, so how to do that? We know that the velocity is displacement over time. Now we need to solve for how long, which is our time. We need time on top. Dividing both sides by velocity, we get time is equal to displacement over our velocity vectors. Okay, so our displacement, velocity, they're in the same direction. Yes, they can be used. These numbers can be used. The pair of numbers that we have are displacement 1462, and I have that saved on my calculator so I can easily access it, over 937.7. I might have to recalculate that one again, per hour. Okay, so yeah, I'm going to have to store this number here. I'm going to store this displacement as alpha s, and then our velocity vector that was taking the square root of our, so Pythagoras over there, 930 squared plus 120 squared. Okay, so we have that, and I can store that too. Store alpha, let's do v. So we have s over v. Okay, 1.559, and notice is not in seconds, it is in hours because we are dealing with kilometers per hour. 1.559 was it? And that's gonna round up to 1.6 hours. Okay. Whew, okay, so that is the time. So just a little bit less than 2 hours to get to Seattle, well, to the same latitude as Seattle. Okay, so that's our first method. The second method that I want to show you has something to do with why it's important to consider components independent of one another. So that's going back to why do we use components? Why are components in physics important? And that has to do with components of the same set of components of certain vectors. They all work independently of one another. Now, what does that look like in this question? You might be wondering, how could I use the 1450 kilometers as a displacement to calculate the same time? Mathematically, you might have thought, oh, I just need to use the 930 kilometers per hour. You are right, but there's a reason why we can do that. And that has to do with the wind and the plane, there being components that are perpendicular to one another. And because they're perpendicular to one another, they don't affect one another. What that means is, imagine you have a plane starting off here. Every hour is going to fly 930 kilometers southward, and also 120 kilometers eastward as well in that first hour. Okay, but in the second hour in the second hour that doesn't change. It's still going to fly 930 kilometers south and 120 kilometers more going towards the east. If you combine that, that's like roughly 1860 kilometers, which is a little bit more because it's 2 hours, right? But you can see how if the plane's going south, it's not going to go south at a larger velocity than when it started with, even when there's wind blowing towards the east. It's not like I'm adding 120 kilometers to the 930 kilometers. And the reason why is because they don't belong in the same axes. Okay? They don't belong in the same axes. They don't add to one another. So if I need to find out how long this plane took to go the 1450 kilometers south, I only need to look at the component of my plane that is going in the southward direction, which is the 930. Okay, only this one is affecting how much it goes south. The wind doesn't care about the plane. It's not like, oh, you're going south, hey, let's give you a boost. The wind's not even going south. You're right. If the wind was going south, it would be a different scenario. Now we have the displacement, and I'm going to label this as displacement in the y-axis direction, and in the vertical direction here. We have this as 14050 kilometers. And we also have the velocity in the y direction as 930 kilometers per hour. Notice I'm using y here as an axis. Only the y-axis vectors will talk to each other. Okay, they're on their own channel. Okay, just like we have our own channels. You know. Okay. So to solve for our time, we have again, and I'm gonna actually copy and paste our equation from above. I don't want to go through that again, because you can just watch it yourself here. So T is equal to displacement over our velocity vector, and we are dealing with the y direction. So here we have time, and you might think, oh, but we might get a different time. Well, just you watch. Heh. So we do substitute all of these in, put in our calculator. 1450 divided by 930, 1.559, bam. 559 rounded up to 1.6, not kilometers, this is hours. Okay, so this is interesting because you're now thinking, hey, the time it takes my plane to fly from A to B is 1.6 hours. In that amount of time, part of my travel was 1.40 kilometers south, 1450 south, and of course that's going to give me the same time, right? Now you might extend it and think, ooh, can I use that same time to find out how much east I have gone? And you are correct. You can use this time to find out how far east you've gone. But with which vector? With the wind vector, of course, right? Because that is the east component. It's the x-axis you're dealing with. So you need to be mindful of which two pairs of displacement velocity vectors you're working with, depending on which axes you're dealing with. Which direction of movement. This is where directions are very important, okay? So that was the second way of dealing with this question, and that considering the fact that vectors work independently of one another, that when they're perpendicular to one another, okay? So using the same kind of reasoning, I would like you to try question B for poor Luke. And again, I can draw this for you just so you have an idea. Poor Luke is swimming across this river, but now we know that the river is 1.0 kilometers, or 1 kilometers, and yes, you might have thought it's 1,000 meters. Yes, it is. How long would it take Luke to swim across the river? Very similar question to the last one. Okay, so again, good time to pause your video. If you didn't quite fully understand what we did before, welcome to go and replay the video from the start, and then try this problem, okay? Okay, here I go. So we have a right triangle, and we have our angle 31 degrees from our previous question. I'm going to do this in two methods. First method here is finding that displacement in that diagonal using the 0.897 meters per second. And to do that, we're going to use our trig, and we have 1,000 meters on the adjacent side. To find our hypotenuse, we use cosine 31, and that gives us our new value. And I'm just going back there to check my values. Just make sure that I have the values that are non-rounded. Is not, and it's 31 point something, which I'll use that in my solutions there. So I get 1,167 meters, which is a little bit larger than the 1,000. And I take that divided by my velocity, giving me my time of about 1,200 seconds. So then the second method I will only use the vertical components. So I have the 1,000 meters, I have my velocity in the vertical direction, 0.83. Divide the two together, I get a time that is also, should be relatively, yes, that is also close to 1,200 seconds. And that's roughly about 20 minutes. 20 minutes. Okay, so here but in terms of level of understanding, if you've done it the second method I've shown you, it shows me you have a deeper understanding of the problems and the concepts at play. So I have a small preference, but I mean, even if you did it this first method, you clearly showed me and you understood the fact that the displacement would be different because Luke is traveling at a diagonal, okay? Now, a couple of things I just want to mention is that I accidentally used the rounded value of Luke's resultant velocity, which gave me a little bit different answer. You might have noticed it's not too different, but it just shows that how you can get very consistent answers if you use the original non-rounded values. So I also didn't want it to make this video too long by going back and saving my answers again, but I did do that for the angle. So alas, I rest my case. So yes, these you might 1,200 seconds roughly about 20 minutes for him to get across the river. I don't know. Can you swim for 20 minutes fighting without getting a break? Well, good for Luke. Good for Luke. Okay, so here is question B, and an extension to problem A, and which also reminds me, if you want to challenge yourself, if you want to challenge yourself with this Luke problem, you can also ask yourself this question here. Assuming Luke's remained in this trajectory and also affected by the current, how far downstream would he have gone after he reaches the other side? How far downstream would he be as a result? You know what? I'm actually gonna post the answer and a general, very brief description of how you can solve that in the comments down below. And of course, you can always ask me in class, or you can send me a message if you want to know exactly how to do it. Otherwise, good luck with the rest of your problem sets. Hopefully you got something out of this video. We will further reinforce the idea of component independency in a later part of this unit. So stay tuned and see you next time on the Fat Mama Physics channel.